So in this video, we're going to start learning to analyze circuits. Now, we just need to know a bit of background knowledge, and the first thing we need to know is that charge is conserved. And we need to know that the sum of all currents entering a junction, in a circuit, so the sum of all currents entering this junction is equal to the sum of all the currents exiting the junction. So these currents, so if this was, 1 amp and 2 amps, and they add up to 3, well then these 3 would also add up to 3. So the sum of these currents, whatever they are equal to the sum of these 3 currents. So the sum of all currents entering a junction is equal to the sum of all currents exiting the junction, where I is obviously measured in currents and the unit of current is in amps. So that's the first thing we need to know. And here's just a quick example showing us. So here we have a battery, it's operating 3 light globes. These are all connected in parallel with one another. So what is the current at points X, Y, and Z? So the way that current works is if we have 6 amps flowing through here, and we have 2 amps branching off here, there's actually going to have 4 amps going through this branch. Because remember, the sum of the currents entering the junction needs to equal the sum of the currents exiting the junction. So we have 4 amps flowing through here. Then when we get to this junction, 3 amps is going through here. So 1 amp must be going through here at position X. So then we keep going. So there's 1 amp flowing through here. So current doesn't slow down when it hits a component. It doesn't slow down. Current in this loop is all 1 amp. From here to here, it's all 1 amp. Now when it meets to this junction here, we have 3 amps flowing in here, and we have 1 amp coming in here. So again, those two current streams are going to join together, and we're going to have 4 amps of current flowing through this little wire here. When we reach this junction here, we have 2 amps flowing through here and 4 amps flowing through here. So at position Z, we're going to have 6 amps again. So all that current flowing through, it's conserved, and it's still 6 amps when it comes around. So that's the flow of current. So the current going into a junction, the sum of all the currents entering a junction is going to be equal to the sum of all the currents exiting the junction. The other thing you need to know is that the potential difference is the same across all loops that are connected in parallel. So we have this green loop and this red loop. So this green loop, so this battery is supplying 12 volts of potential difference. And each loop connected in parallel is also going to get 12 volts. So there's 12 volts through the green loop, 12 volts through the red loop. And what you also need to know is that the potential difference across a battery, so we have 12 volts across here, that's going to be equal to the sum of the potential differences across components in series. So what I mean by that is we have 12 volts going through this green loop. So there's going to be some sort of potential difference drop across this component and some sort of potential difference across this component. And these two potential difference drops are going to add up to 12 volts. So technically that's Kirchhoff's voltage law. You don't really need to know that part. You just need to be able to use it. So using Kirchhoff's voltage law, determine the potential difference drops, V1 and V2 in the circuit shown. So obviously this battery is supplying 9 volts, So in this top loop we have 9 volts, so this is 9 volts. And in this loop here we also have 9 volts, so we have 9 volts through the whole thing. So if we wanted to work out what this is, well obviously if there's 9 volts through the whole thing and there's 4 volt drop across this component, then across this one there's going to be 5 volts, because 5 plus 4 is 9. Now we're going to start analysing some different circuits. To begin with, we're just going to analyse series to keep it simple. So this is a series circuit. We have 3 resistors in series with one another. Now you need to know that the potential difference across each resistor adds up to the total potential difference. So say, for argument's sake, we had 12 volts from this battery of potential difference supplied, then this voltage drop and this voltage drop and this voltage drop are all going to add up to 12 volts. And just recall that the potential difference is a measure of the electrical potential energy per coulomb of charge. So what happens is this battery supplies electrons with 12 volts. And what happens is, as the electrons move around the circuit, they transfer some of their energy to this component. Okay, so there's going to be some sort of voltage drop, and then the electrons are only going to be carrying a certain amount of energy. And then when they go through another component, there's going to be another voltage drop, and they're only going to have a little bit of energy. And then they're going to pass through this third component, and then they're going to have transferred basically all their energy, and then they're going to travel back to here. And basically, the battery source is going to provide the electrons with energy again when they're moved from one side of the terminal to the other, and then it's going to keep flying around and transferring their energy as they go through the circuit. And the energy is transferred Now, in a series circuit, the current is equal everywhere. So the ammeter reading for current at positions 1, 2, and 3 are all going to be equal to one another. So current through a series circuit are all going to give you the exact same value. So current is equal in a series circuit. So the total voltage is equal to the voltage drop across the three components, which will be on your formula sheet, and then the total voltage in a series circuit is equal to the same at all points in a circuit. And then the final thing is that you need to know that the total resistance in a series circuit is equal to the addition of any resistors in the circuit. And you also can be required to use Ohm's law in order to analyze specific components across a circuit in series. So, just a couple calculation examples. So, super straightforward. We have a 100 ohm resistor, a 300 ohm resistor, and a 1 kilo ohm resistor, and they're connected in series. What is the total equivalent resistance? So basically we're trying to find the total resistance, and the total resistance is literally just the sum of the resistors. So it's going to be the 100 ohms plus the 300 ohms plus 1 kilo ohm, and remember kilo ohm just means 1,000, so that's 1,000 ohms. So 100 plus 300 is 400, plus 1,000 is 1,400. So resistance in a series circuit, straightforward, just add the resistors together. Now, again, state the total resistance in this circuit. So we have a circuit, we have a 20 volt power supply, positive terminal, negative terminal, 20 ohm resistor, 30 ohm resistor, 40 ohm resistor. So the total resistance is just going to be 20 plus 30 plus 40, which is 20 plus 30 is 50, plus 40 is 90 ohms. So we have 90 ohms of resistance through this circuit. So calculate the current flowing through the circuit. So Ohm's law, well, the way I like to remember it is V equals IR. And then to calculate the current flowing through the circuit, so the current is voltage divided by resistance. Current is voltage divided by resistance. So we've got a voltage of 20 volts divided by a current of 90 ohms. So 20 divided by 90 is about 0.22. So 20 divided by 90, is 0.22. And current is measured in amps. So it's 0.22 amps. Now calculate the potential difference across each resistor. So there's 20 volts in total. There's going to be a voltage drop across this resistor, a voltage drop across this resistor, and a voltage drop across this resistor. So to work out the voltage drop across each resistor, we need the current times by the resistance. So let's just call this position 1, position 2, and position 3. So the voltage drop across position 1 is going to be the current. Now remember, in a series circuit, the current is the same everywhere. So everywhere in the circuit, we're going to have 0.222 amps of current. So it's going to be I times R. So it's going to be 0.222 recurring multiplied by 20 ohms. So 0.222 recurring times 20 will give us 4.44. And that's in volts. So 4.44 volts across that one. The voltage drop across our second resistor again will be 0.222 multiplied by 30. So 0.222 multiplied by 30 will be 6.66. and that's in volts. And then finally, the voltage drop across our last one is going to be 0.222 times by 40. And that's going to be 8.89. And that's measured in volts. So the total voltage drop is 20, so we're going to have our 4.44 plus our 6.66. I guess that's 6.66 recurring, so it's 6.67 technically. And our 8.89. And if you add them all together, you should get 20 volts, which you do. So just super quickly recapping, in a series circuit, the total voltage is equal to the voltage across any components. Okay, the addition of any components. The current is equal everywhere in a series circuit, and if you want to work out the total resistance, you just add the resistors together. And you can be required to use Ohm's law to calculate current or resistance at any point in time, like I have. So I used it to calculate the current, because I worked out the resistance and I had the voltage, so I could work out the current. And then you can actually use Ohm's law to work out the potential difference drop across different components. So now I want you to have a go at those questions in your booklet. Cheers.